There are theorems in geometry that are very easy to understand the formula and how to plug and chug, but sometimes you don't understand the use or the application of that theorem. In my opinion, the intersecting chord theorem is one of those examples. It states that if you have a circle, and it doesn't matter what the radius is, and if you take two separate chords and have them intersect somewhere in the circle, and they do not have to intersect on the center. What the theorem states is those chords are broken up into smaller segments, and there's a property that A times B is going to be equal to C times D. Now in this video I'm not going to prove why. You can easily look that up in another video. It deals with similar triangles. In this video I'm going to tell you how to apply that. Earlier I mentioned it does not have to go through the center of the circle, but let's say the two chords intersected at the center. One thing you should notice quite clearly is the chords are broken up into 4 segments, and each one of those segments happens to be the radius of the circle. So when you have A times B equals C times D, what you're really getting now is radius times radius equals radius times radius, which is obviously a true statement. A lot of times this theorem is then produced into these type of math problems found in textbooks. You have a circle, you have two chords, and they're already broken up into lengths of a 2, 4, 8, and an x, and all the question says is solve for x. And so learning the theorem of A times B equals C times D and pattern matching, you could do 2 times x equals 4 times 8. Now instead of using an x for a multiplying, I'll use a dot. 2 times x equals 4 times 8. 2x equals 32. Divide by 2, x equals 16. This is nice and dandy, but there's no application of it. And a lot of textbooks go problem after problem after problem of these type. I call these plug and chug. Now I want to look at a problem which I call a think and link. So I have a window that I'm going to install high up on my wall. I know a couple things about it. I am going to have it stretch out 16 feet. So the width of it's going to be 16 feet. The height of it is going to be 4 feet, and it's going to be in the middle of my width. So right there is going to be 4, where, as I mentioned earlier, that's 16. And the border of the window comes from a circle. So somehow I'm going to try and make a circle that swoops through those dimensions. More visually, let's put this on a coordinate grid. And let's say my points are 4, 7, 12, 11, and 20, 7. Things to notice from these points is the width here from 4, 7 to 27 is 16, as I drew earlier. And centered on that makes a width of 4 right there. And my goal is somehow to place a circle connecting those 3 points. So I want to make a circle, I'm just going to guess here a little bit, and try and get it, that's not too bad, to connect through those 3 points. Now, let's officially write out that goal, and let's do a quick reminder of what an equation of a circle is. So, our goal, find the equation of a circle that helps create the border of the window. And what that has is 3 points that are going to be on the border of the circle. And it's true that any 3 points that are non-collinear will make a circle. So we can find this somehow. The other thing I want to give you is a reminder of the equation of a circle. It is x minus h squared plus y minus k squared equals r squared. And the radius is the r, and the h comma k is the center of the circle. Now, a good way to visualize this is using Desmos. What I've set up so far is the 3 given points, 4, 7, 12, 11, and 27, and I'm showing you the window. It's the shaded red region. My goal is to slide around h, k, and r, the variables inside the equation of a circle, to fit this window. Let's first start by sliding around the h. This shifts the circle left and right. As I shift, I know I want to move to the right here, and I'm going to center it around that 12, 11 just based off the symmetry. Now my next instinct is to slide up the k so that my top of my circle is the top of the window. And now I hope to just stretch it out with the larger radius and have it fit. But what you notice is as you stretch out, the radius gets bigger, which actually increases the top part of the circle. So I'm going to need to shift this back down now to try and counter the increasing radius. And this looks pretty close. I'm just a little bit short on size. So let me increase again. And let's see if I can move it around and fit it. So Desmos helped me see shifting left, right, up, down, and increasing the size of the circle, how to fit it. But I want to show you how to do that using the theorem that we started with today. So I put the circle onto my whiteboard here, and we're going to try and visualize the chords. So I'm going to connect the 4, 7, and the 27. And I'm also going to connect the 12, 11 down to the bottom. So I have the chords, and I know some of the numbers, but not all of the numbers. Earlier I told you the height of the window was going to be 4. So I can put a 4 there. And I told you originally that the total width was going to be 16, but since it's symmetric, that can be broken up into an 8 and an 8. Now the question is, what is the bottom part of that chord worth? So I have a 4 and an x, an 8 and an 8. So we can set up 4 times x equals 8 times 8. I have 4x equals 64. Divide by 4, x equals 16. So now I know this width right here is 16. From that, I can talk about finding the diameter of the circle. So the diameter of the circle I will highlight from the very top to the very bottom is that green chord, and I have a 4 and a 16 to it. So I now know the diameter is worth 20, which would mean the radius, which is half of the diameter, is worth 10. From what we found on Desmos, R was 10. Now if you're still looking to find the center of the circle, realize you're starting at 12, 11, and if I need to find the center, I need to walk down 10 units. So to do that, I'm starting at x equals 12, y equals 11, and I'm just going to move down 10. That means my x doesn't change, but my y does. So my center of the circle is 12, 1. So we have found the equation of the circle using Desmos, and we've also found the equation of the circle by hand using the intersecting chord theorem. So hopefully this is a way to see how you can apply a very basic theorem into a more application-based problem. The sun rises every day, and as it rises above the horizon, it makes me wonder if we could use the intersecting chord theorem to discover some properties of the sun. Let's assume the sun is a perfect sphere, so in 2 dimensions it's a perfect circle. And if we could stare at the sun, we could notice the length of the visible sun on the horizon. We could measure the height of the visible sun above the ground. And with that, could we discover the radius and the center of the equation of the circle for the sun?